This is the third lecture on introductory quantum computing. So today I'll talk about inner products and unitary transformations. So before getting started on the new topic, let's work out an example from the topic we discussed in the last lecture, namely systems of multiple qubits and tensor products. So let's do this example. So we're saying, suppose we have two single qubit states, and they're pretty general. So two states we can represent by two angles on the block sphere. So let's say the states are, we have psi1 equal to cosine theta 1 over 2 plus e to the I phi 1 sine theta 1 over 2. So this multiplies 0, this multiplies 1. And then psi 2, again, something similar with angles theta 2 and phi 2. Then let's consider the state, a two qubit state, psi, that's given by some normalization constant. Then I have psi 1 for qubit A, psi 2 for qubit B, minus psi 2 for qubit A. So this the second single qubit state is the state of the first qubit now, qubit A, tensor psi 1 for qubit B. Okay, so the problem first is saying find n, so the state is normalized. And then the question is, what is the probability of getting 0 for the state, let's say state of qubit A upon a measurement of, let's say, both qubits in the computational basis. Okay, so how can we make progress on this? Well, first, I guess we have to calculate the state in the computational basis. And then we can make sure it's normalized. And then from that, we can extract the needed probabilities. So there are two ways to do this. So let's do both ways. So one way is just to do it using this notation. So just do the tensor product and expand them out so we get the result in the computational basis. So let's do that. So I can write psi to be equal to n, and then let's multiply cosine theta 1 over 2, 0, plus e to the I phi 1 sine theta 1 over 2, 1. We tensor that with cosine theta 2 over 2, 0. So the first 0 is for A, right? These zeros and ones are for A if we want to be very explicit. They appear first. And these are for qubit B, as you can see. Plus e to the I phi 2 cos or sine rather, sine theta 2 over 2, 1. And then from this, we have to subtract the tensor product where we've switched 1 and 2. So now I have cosine theta 2 over 2, 0 of A, plus e to the I phi 2 sine theta 2 over 2, 1 of A, tensor cosine theta 1 over 2, 0, B, plus e to the I phi 1 sine theta 1 over 2, 1, B. Okay, so now let's continue with this. So then this state becomes psi is equal to n. So let's expand it out. So 0 tensor 0 has a coefficient that's product of the cosines. So I have cosine theta 1 over 2, cosine theta 2 over 2, 0 of A, 0 of B, which I represent by 0, 0. Then let's say 0 of A, 1 of B. So that's going to be cosine theta 1 over 2, sine theta 2 over 2, e to the I phi 2. Then that's 0, 1. Then I multiply this one, 1 of B, with 0 of 1 of A. The first one is A, the second one is B. 1 of A, 0 of B. So that's going to give me cosine theta 2 over 2 sine theta 1 over 2 e to the I phi 1. And that's 1, 0, 1A, 0B. And finally, we get the two ones, 1A, 1B. So that's going to be sine theta 1 over 2 sine theta 2 over 2. Let's continue here. E to the I phi 2 plus phi 1. And then I have the state 1, 1. So from this, I have to subtract this other tensor product. And that other tensor product, the only thing that's happening to it is that 1 and 2 are switched, essentially. So here I have cosine theta 2 over 2, cosine theta 1 over 2, 0, 0. Then here I have cosine theta 2 over 2 sine theta 1 over 2 e to the I phi 1, 0, 1. Then I have minus cosine theta 1 over 2 sine theta 2 over 2 e to the I phi 2, 1, 0. And minus, let's write this term here, sine theta 2 over 2 sine theta 1 over 2 e to the I phi 1 plus phi 2, 1, 1. So you see that the state 0, 0, the coefficients cancel out. They're symmetric in theta 1 and theta 2. Similarly, the state 1, 1, the coefficients cancel out. So we're left with, let's say here, let's consider the 0, 1 state. The coefficient is going to be cosine theta 1 over 2 sine theta 2 over 2 e to the I phi 2 minus minus cosine theta 2 over 2 sine theta 1 over 2 e to the I phi 1. So that's now the coefficient of 0, 1. And then for 1, 0, what we're going to get is, well, let's write it. It's going to be plus cosine theta 2 over 2 sine theta 1 over 2 e to the I phi 1 minus from here for 1, 0, we're getting cosine theta 1 over 2, sine theta 2 over 2, e to the I phi 2. And this is multiplying 1, 0. So you will see that these amplitudes are the same up to a sign, right? This is a negative sign of the other one. So if I keep going, I can write my state psi. I can write it as n times this coefficient, all of that, cosine theta 1 over 2, sine theta 2 over 2, e to the I phi 2 minus cosine theta 2 over 2, sine theta 1 over 2, e to the I phi 1. And then this multiplies 0, 1 minus 1, 0. So that's my state. Then, the problem doesn't really specify that n has to be real. If n were real, you would just find the absolute value squared of this. So in general, suppose, I find some state that in the computational basis is given by, let's say, n and sum over n cnn, right? So I have some numbers, I have this n, and n is the normalization constant. So then I'm going to require that the state is normalized, which means n squared sum over n cn squared is 1. So that means that n squared is 1 over this sum. And then I can say n is the square root of that. But n doesn't have to be real as long as, so absolute value squared of n here is equal to that. We're good. So it's kind of the easiest way to proceed now is to just say, well, if my n has something that just cancels out all of that, then I'm left with state 1, 0 minus 0, 1. And then I have two coefficients that are 1. So then I can normalize that by just writing 1 squared plus 1 squared is equal to 2, and then dividing that by dividing that by just square root 2, or multiplying that by 1 over square root 2. So from here, one solution, it's not unique. It's because you can have an arbitrary phase. It's just the magnitude of n that matters. But one solution is to simply cancel that out. So let's write n as 1 over all of that minus that's some complex number, and then multiply that by 1 over square root 2. So if n is this, right, then my state becomes 1 over square root 2, because this cancels that numerator, 0, 1 minus 1, 0, and it's very easy to see that 1 over square root 2 squared plus 1 over square root 2 squared is 1, so this state is properly normalized. So we just found our n, and it's quite interesting that the state, even though we had these two arbitrary states for the individual qubits, when we construct this particular combination, just becomes a standard singlet state that's independent of all the angles. Okay, so now the problem is saying, what is the probability of getting 0 for state 1? So if I perform a measurement, right, with probability 1/2, so let's do state probability. So if you consider all of them, you have 0, 0, you have 0, 1, you have 1, 0, you have 1, 1, And these we don't get. These have probability 0 because they don't appear in this superposition. And these, they appear with a coefficient of 1 over square root 2 or minus 1 over square root 2. You square that, it's going to be 1/2, 1/2. So if I get this, A is 0. If I get this, A is 1. So let's say 0 of A is just 1/2, which I can read off from here. Okay, so that's the algebraic way of solving this problem. We could also use the matrix notation. So that's going to be quite helpful as well. Essentially, it's the same calculation, but kind of rearranged in a different way. So if I want to write, again, we're saying psi is n 1A tensor tensor 2B minus 2A tensor 1B. So I can use kind of the directly work with the representation and say, well, then the representation of psi as a column vector is going to be n. And then I have psi 1, which is cosine theta 1 over 2, e to the I phi 1 sine theta 1 over 2. Then I do the tensor product, cosine theta 2 over 2, e to the I phi 2 sine theta 2 over 2, minus switching 1 and 2, which is cosine theta 2 over 2. So this state now is the state of the first qubit, qubit A. So it appears first in the tensor product. Tensor cosine theta 1 over 2, e to the I phi 1 sine theta 1 over 2. And then essentially we would do the same thing, right? So we're going to get, for this tensor product, so I have this element multiplying the second matrix. So I'm going to get cosine theta 1 over 2, cosine theta 2 over 2, cosine theta 1 over 2, e to the I phi 2 sine theta 2 over 2. Then you have this element, so e to the I phi 1 sine theta 1 over 2 multiplying first cosine theta 2 over 2. And then here I'm going to get e to the I phi 1 sine theta 1 over 2 e to the I phi 2 sine theta 2 over 2. That's it. And then you subtract the term with, let's say, 1 going to 2. The same expression with 1 going to 2. And you would see that the first and last element cancel out. And for the two middle elements, we're going to get what we essentially calculated before. So we're going to get this, and it's negative. So that's an alternative way of doing the problem. It's a little bit more compact when we work with these matrix representations and use the recipe for tensor multiplication. Okay. So let's switch gears and talk about the new topic for today. So inner products. And unitary transformations. So this is essentially two topics. So first, let's talk about inner products. So just to review, when we had vectors in in real space, like geometric vectors. So again, take a two-dimensional space, x and y coordinates. We can have vectors live in here in this space. So let's say vector A, vector B. And we have the basis vectors I and J. And they have some components. So for example, A, let's say, is A sub x I plus A sub y j, and B is B sub x I plus B sub y j. We had the inner product defined for these vectors, which in terms of the components in this fixed coordinate system can be written as ax bx plus ay by. So the geometric representation is you would take the component of one along the other one. So if this is A, this is B, I would project B along A or project A along B, and then multiply this length by the length of A. So essentially, it's like the product of the two lengths times the cosine of the angle between the two vectors. So we had two important cases. So when A is normal to be perpendicular to B, then there is no component in the direction of A, so the inner product is 0. When A is parallel to B, they're in the same direction. A dot B, if you take its absolute value, it could be positive or negative depending on the direction, but that's essentially the length of A times the length of B. And a particular case of this is if you take the inner product of a matrix by itself, the length of a vector by itself, the length of the vector squared is just the inner product of the vector by itself. So these notions generalize to the complex vector space corresponding to systems of qubits, which is two-dimensional for 1 qubit, four-dimensional for 2 qubit, eight-dimensional for 3 qubits, and in general, 2 to the n dimensional for n qubits. So already we had this notion of the normalization of a state, and that in some sense is analogous to the length of the vector being 1, right? The normalization, we're taking the individual amplitudes, we square them up to this complex conjugation. So we take the absolute value squared because they're complex numbers and add them up. So that's quite analogous to the length of a vector, right? So if I have again this vector A written as AXI plus AYJ, the length of this vector squared is going to be AX squared plus AY squared, which is the inner product of the vector by itself. So let's use a more compact notation. So we can give just a number label to all the basis vectors. So let me give an example. So for example, let's say I have 4 qubits. I have 0, 0, 0, 1, 1, 0, 1, 1. And just arrange them this way and then just call this state state 1, call this state state 2, call this 3, call this 4. You can always do that. If I have 3 qubits, I can write 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Can always give a name to these. Call this state 1, call this 2, call this 3, this 4, 5, 6, 7, and 8. Okay. So one thing you may notice is that this is just the, if this string here is interpreted from right to left, is the binary representation of a number, this is just that number plus 1. So 0, 0, 0 is the binary representation of 0. So you add a 1 to it, that becomes the first state. So this 1, 0, 0, 0, it's the binary representation of 1. So that becomes 2. 0, 1, 0, binary representation of 2, right? It's 0 times 2 to the power 0 plus 1 times 2 to the power 1. So that becomes 2. This is the binary representation of 3, if you read it from this way. This is the binary representation of 4, right? It's just 2 to the 2, 2 to the 0, 0 times 2 to the 0, plus 0 times 2 to the 1, plus 1, 2 to the 2. The next one, etc. So we can always arrange our states like that. And in general, write in this notation, write psi as sum over n, alpha n now. So, and this one integer is shorthand for that sequence, times the state n. And the normalization is sum over n, alpha n absolute value squared is 1. All right. So I can write that normalization condition like this. Alpha n complex conjugate times alpha n. That's just the absolute value of alpha n squared. So this motivates us to define an inner product that looks like this. So if I have, let's say, state psi 1 given by, or let's say psi given by sum over n alpha n n, and consider another state psi prime given by sum over n alpha prime n n. Inner product of psi and psi prime is denoted by, so this is just a notation at this point. I write the first one, but I flip this bracket, so I do it like that. This is given by sum over n alpha star n alpha prime n. So then the normalization condition in this notation is just the inner product of a vector by itself, of a state by itself, is 1. So that's a general inner product between two vectors. So let's do a quick example here. So take, let's say we do, let's say psi 1 is, I can do 1 over square root 3 times e to the I pi over 4 times 0, 0 plus 1 over square root 3 times 0, 1 plus 1 over square root 3 times 1, 1. And let's say I have another state that's, say, 1 over square root 2 e to the I pi over 4 times 0, 0 plus, let's say, 1 over square root 2 e to the minus I pi over 2, 1, 1. So those are two states for a system of 2 qubits. And what happens if I want to calculate the inner product psi 1, psi 2? I'm going to get, for the 0, 0, I have to take the complex conjugate of this, multiply it by that. So I'm going to get 1 over square root 3 e to the minus I pi over 4. And multiply that by 1 over square root 2 e to the I pi over 4. The next state is going to be 0, 1. But for this one, the coefficient of 0, 1 is 0. So I'm not going to get anything. The next one is 1, 0. For 1, 0, the coefficient is 0 for both. So I'm not going to get anything. And the last one is 1, 1. So I take the complex conjugate of this real number that's the same times this number here, e to the minus I pi over 2. And that's my answer. So it's going to be here, these guys cancel out. So it's going to be 1 over square root 6 plus 1 over square root 6. And e to the minus I pi over 2, let's just visualize it quickly. So minus pi over 2, start from here, from 0 as a minus. So you go clockwise, you go that way. So it's going to be this point here. And that's minus I, right? So its cosine, which is the real part, is 0. Its sine is minus 1. So again, reminding you, e to the I alpha is cosine alpha plus I sine alpha. So this is just minus I here. So this is going to be 1 over square root 6, 1 minus I. And that's the inner product that we found. Okay, so again, we can do this in terms of matrix multiplication in a kind of a nice way. So essentially, if I now let's take the very same example and say I write my psi 1 as a vector in this basis. So my psi 1 is represented by 1 over square root 3 to the I pi over 4. One over square root 3, 0, and 1 over square root 3. Okay. And my phi 2 is represented by 1 over square root 2 e to the I pi over 4. Zero, 0, 1 over square root 2 e to the minus I pi over 2. So this sum corresponding to the inner product, I can always write it as so I'm multiplying the complex conjugate of this by this, the complex conjugate of this by that, etc. So I can arrange these complex conjugates in a row and then use the rule of matrix multiplication. Right, that would give me the same sum. So this motivates defining a dual state. So if I have some state that's defined as, let's say, sum over n alpha n n, I can from this define a dual, so give a meaning to this thing that multiplies psi2, and write it as sum over n alpha n star, and then I can also flip the order for these basis states. And if this has a column representation alpha 1, alpha 2 up to alpha, the last one, let's call it m, which in general for a system of qubits is going to be 2 to the n, where n is the number of qubits. This has a representation as a row. And then I have alpha 1 star, alpha 2 star, up to alpha m star. All right. So far we've talked about the inner product between two states, and the inner product naturally motivates defining these dual states that allows us to write the inner product as just the matrix product when working with the representation of states in the basis, which is analogous to working with components of a vector in some fixed coordinate system. So then the last thing that I want to mention in this lecture, and will of course continue throughout the course when talking more about quantum circuits, is the notion of transformation of states. So suppose you have a quantum computer, it's comprised of a bunch of qubits, but also it has ways of manipulating these qubits. So letting qubits interact or applying some fields to the qubits. Essentially, as the quantum computer operates, the system comprised of the qubits, which is the entire computer, evolves according to the laws of quantum mechanics. So these states transform, and that transformation encodes the computation that we're trying to perform. So the nature of these transformations, according to the laws of quantum mechanics, is that they're linear. So anytime you transform a state using quantum coherent evolution, you drive it in some way, or you let the qubits interact in some way that we control, the final result is a linear mixing. So you can always represent that by the multiplication of a square matrix under representation of the state. So transformations. So let's say you have a state psi, and you do some stuff to it, and let's suppose that's the state of the entire system. So if you have n qubits, you're going to get a matrix. So let's say that's the state that you represent by an m by 1 column vector. There's going to be some m by m matrix that acts on it and transforms it. So suppose, I don't know, just take one qubit, let's say size alpha 0 plus beta 1, which you represent as alpha beta, U in general is going to have a representation that looks like this: U11, U12, U21. It's going to be some 2 by 2 matrix, U22. So then the state U times psi will have a representation that just comes from matrix multiplication of this by that. So it's going to be U11 alpha plus U12 beta plus U21 alpha plus U22 beta. Now, in addition to being linear, this transformation preserves the norm. So if you have a normalized state and you transform it, we should conserve the normalization. So that makes these matrices U kind of special. It makes them so-called unitary. So we'll elaborate more in the next lecture, but essentially, we write it, U is unitary to preserve normalization. So essentially, the Hermitian conjugate of a matrix is defined by transposing it and taking the complex conjugate. So if you have U is equal to U11, U12, U21, U22, then Hermitian conjugate, which we represent as a dagger here, is first I transpose it. So I write it as U11, U12 comes here. So the first row becomes the first column. And then the second row becomes the second column. So U21 and U22. And then complex conjugate every element. So that's how we construct the Hermitian conjugate. And the unitarity means that U times U dagger is equal to U dagger times U is equal to the identity matrix. So I is just, for a 2-dimensional system, it's 1, 1. For any m-dimensional, it's just ones on the diagonal and all other elements are 0. So this constraint and these linear transformations guarantees that the inner product essentially is preserved. And these are the types of transformations that arise from quantum evolution. So all that happens in a quantum computer. So when we construct circuits, develop algorithms, it's just creating some unitary matrix in some way. Okay, this is a good place to stop.